Memoization is a programming technique with the purpose of improving a function's performance by caching results. So if the same input value is provided, you can return the results quickly without going through the heavy computations again. In this tutorial, we are going to look at patterns for memoization in JavaScript and then look at an example of what it can do for you. So an application example for memoization is if you have a function that does a lot of computations, and it is a pure function, meaning each time the same input value is provided, it will return the same output value, then it is a good candidate for this. Now, you may be thinking, well, duh, all my functions are pure functions, but don't be quite that quick at making that decision. If your function relies on data outside of itself, that data could change and affect the results. Let me show you an example. This very simple function here is not pure because it depends on this variable, this global variable, which is outside the function. And if that were to change, well, then the results that the function produces, even though the same input value, say a 3 was sent in, what it returns could be different based upon what this num variable is. So that's not a pure function, where this would be. Every time a 3 is entered, it will return the same value. So if these two items are true, if it's heavy with computation and if it's a pure function, then it's a candidate for implementing memoization. The idea is that because the computations are intensive, you can store an output value that has already been achieved, and then the next time the function is called with the same input value, you can simply return the stored value without going through all the computations. Memoization is a term that may be difficult to remember. Now, the way I remembered it when I first encountered it is that the term is very close to the word memorization. And since it refers to keeping track of values, I use that similarity to help me remember it. Maybe that will work for you as well. Now, there are a couple of patterns for implementing memoization. One uses closure, which we will look at towards the end of this tutorial. The other pattern I think is easier to learn, and so we will look at that first. This pattern uses the function as an object, which it is, of course, and stores the cached value on that function. This prevents us from using a global variable to store it. By the way, I learned this first pattern in Stoyan Stefanov's book, JavaScript Patterns. So let's take a look at that first. Let me remove this code here, and we are going to create a function. It will have one parameter that can be passed in. Now we'll look at an example of what you do if there's more than one parameter later, but this first example, I just want to use a single parameter. Now, first thing we're going to do is an if conditional. And in this if conditional, we're going to check to see if, notice that we're pointing to the function there, if the variable that contains that function dot memo cache, and then in square brackets, the parameter, if that doesn't exist, if that's undefined, then we're going to go ahead and do the computations. So that's the basic structure of it. Now, down below the declaration of this function, I want to do this. I'm just going to set up that attribute which I've attached to the function object. I'm just going to set that up as an empty object. And so you can see with this if conditional, what it's going to do is it's going to look at that object which is attached to the function object, and it will look for an attribute of this parameter that's been passed in. If it doesn't exist, then it'll go ahead and do the computations. Now let's look at what we do inside of here for the computations. First off, we're going to return some result. So I'm going to set that equal to an empty object. Then whatever the computations would be, I'm not going to put a bunch of computations in here. That would go next. And then finally, we would attach to our memo cache attribute using parameter as an attribute for that object. We're going to attach to that the result. So as we're figuring out the computations, we assign them to result, and then they get attached here. This allows it to store that value so that if that value is ever used again, if that parameter is ever used again, this part will not execute. But the final line will, which is this. So basically, we return this object that is attached to our function object and this attribute of that object. That's what we're returning. So we could have, through a particular session, we could have numerous values that are passed into this function, and it would store them. It would store them in one place. If we ever called for them again, it would find them and return them immediately without executing the computation part. So now, just so we can see this working, I'm going to just enter a console log statement and just indicate that the value is being computed here. And then let's just modify the result value. We're going to set the parameter attribute equal to the value that's passed in. So this is the first pattern. We're using the function as an object to attach to it an empty object, and then as values are passed in, we attach to that empty object those different values. We do that right here. If the value already exists, we simply return that value by grabbing it right here. All right? So let me refresh, and let's just look and see how this works. I'm going to open the console. First, I'm going to execute the function with a 5. Notice that we get the console log statement commuting it here. Now, if we execute that function again with the same parameter value, our results that are returned are the same, but we don't go through the computations, which is what this console log statement is showing us. And if those computations are intensive, that can save us some processing time. All right, so that is the first pattern. Now, what happens if we have more than one parameter that gets passed in? How can we use this same pattern? Well, let me address that really quick. I'm going to change this so that we have a second parameter passed in. And right here, what I'm going to do is I'm going to borrow a method from the array object. So I'm going to the prototype of the array object, and I'm getting the method slice. And I'm just going to put it in a variable here so it's easier for me to use. Now I'm going to use that method. Let's do that next. I'm going to use this to create a key. So we're going to create a key that will be put on this object, the same object here. And that key will contain both parameters. So that's the idea here, is that the key will now be for both of them. So if one parameter is the same that we pass in, but the other one's not, it will do the computations. If they're both the same that we've already passed in before, it will not do the computations. It will return the value. So here's how we're going to compute that key. We simply do a JSON.stringify. The reason we're doing that is we want to convert this to a string so that we can use it as an attribute name on this object. Then we use our slice, and we call that method and pass in the arguments from the function. So these are the arguments that were passed into the function. Now, what slice does, the method slice on array, is it returns another array. It acts on the current array and returns another array. And usually it's a subset of that array. But basically what we're doing it here is we want it to act on arguments and return an array with all those arguments. Now, arguments is array-like. It's not an array, but it's array-like. So we're able to make this happen. So we return that as an array, and then we stringify it using the stringify method of the JSON object. So that's what we're doing there. And by doing all of that, it turns it into a string. This key becomes a string. And that allows us to store it. So I just need to change these to key. And then also, let's just modify our results so we can see the difference when we test this. All right, let's save that and let's try this one. So I'm going to refresh that. And this time we will be calling it with 2. So first time we'll call it with a 5 and a 6. We get the log statement computing it here. So it's doing the computations, and this is our return result. Now if it gets called again, it doesn't do the computations, and this is our return result. But if we were to invoke that function with different value, then of course it would go back to computing it. Now we have 2 values stored within that key. If we execute it again, it just returns the value without computing it. So that is a pattern for memoization which you can use if you have a function that's doing a lot of computations. Now before we finish up, I want to take a look at an example that shows what memoization can do for you. A common solution that I've seen memoization used for is a recursive function that determines a Fibonacci number. Now, the Fibonacci sequence is a series of integers beginning with 0 and 1, in which each number is the sum of the previous 2 numbers in the series. So a Fibonacci number is that final number in the sequence. So if I wanted the Fibonacci number for a sequence of 20, I could use this next example to get that. Now, I've seen this example used by Douglas Crockford in his book, JavaScript, The Good Parts, as well as Shelley Power's book, JavaScript Cookbook. But I've also seen it in blog posts. So it is an example that is used a lot when talking about memoization. Now, in addition to this example showing you the power of memoization, it will also show another pattern for memoization. This pattern uses closure to store the cached value instead of attaching it to the function object. Now this example uses more advanced concepts that you may want to review. I've created tutorials on many of these concepts, so if you want to review those tutorials, I will include a link to them in the description section of this video. So first, let me paste in the example that shows the pattern. Then I will describe it, and then we'll take a look at how it helps us. All right, I'll replace the code that we already have here and paste this in. So here is a function, Fibonacci. And the first thing we have inside the function is we've declared a cache variable. And we've set it equal to 0 and 1. Now remember, 0 and 1 are the first 2 numbers of a Fibonacci sequence. So we might as well put them in as already having those values. So we're going to store all of the different values that can come from a Fibonacci sequence in an array. And so the first Fibonacci number would be 0. The second Fibonacci number would be 1. The third would be 1 as well, but that has not been computed yet. So this will set up where we're going to store the values that we will access if we need to. Now notice what we're doing next. We're declaring another function expression. Now this function is going to be returned. And so it will be the function that is called when we use this variable to invoke it, the Fibonacci variable, because this function is returning another function. Now let's look at the function that's being created that is going to return. This function is the one that determines the Fibonacci number. And let's look at how it does that. Now before we look at how it does that, I want to explain how this pattern works for memoization. This function and this variable are both declared within the same function, this Fibonacci function. Therefore, they are of the same scope. Here is the block for both of these variables. So they are of the same scope. So because of that, this function will have access to this cache variable anytime it executes. That's closure. Because of closure, it will have access to it. Even after this function has executed, returned this function, when we then invoke this function, it will still have access to this. That's the power of closure. So that's how the memoization is going to work. Now let's take a look at the function that's being created that will determine the Fibonacci number. And it will determine it using memoization. So first, we let the result equal cache and whatever is passed in. So remember, this is an array. Cache is an array. So we then check if type of that is not equal to number, well then we need to figure it out. So if this is not a number yet, we need to figure that out. So that's where we do it right here. And we do it with recursion. Notice we are calling that same function again. It's with the number -1 and the number -2, and we're adding those two values to get together to give us that last Fibonacci number. And then we set the result to the position in our cache array where it should be based upon what was passed in. All right? Now, with this recursion, I don't want to take a lot of time to explain recursion because I do that in another tutorial. But with this recursion, it will continue to call that function with different numbers. And those will be cached. Those will be stored using that technique of memoization. Finally, when it's all done, we return the result. All right, so that's how it works. Now, I want to show you the value of it. So the way I want to do that is I'm going to include a function that does not use memoization. And then we're going to time how long it takes to use both of these to do some computations. So first, I've just pasted these in. This is the function that does not use memoization. It uses recursion as well. So basically, when it's less than 2, it returns the number. Otherwise, it calls itself with different values. Okay? But nothing is stored. Nothing is cached. Now, this is how we're going to see the value of memoization. We're going to use console.time, and we have a label here, and then console.timeEnd. So what it's going to do is it will show us how long it took to do the computation. Now, what's the computation? We're going to go through a loop of 0 to 20, calling each of these functions. The first one is the non-memoized function, this one here. The second one is the Memoize function, Fibonacci up here. And they're both going through it 20 times. And so we're going to see how long it takes for each one of those. All right, so let me save that. And let me jump out. We'll refresh. So you can see it's returning the final number in the Fibonacci sequence. That's what we're getting. That's what it's showing up here. All right. Now, first, the function that does not use memoization took 5.76 milliseconds. The function that did took 1.9 milliseconds. Now, you may say, well, that's not a huge number. But we're looking at a threefold increase. Now, let's look at what would happen if we increase that number. We're going to go 30 now. So 5.3 milliseconds for memoization. Up here, 51.9 milliseconds. So you can see that as the higher that number is, the more intensive the computations are. And so it's taking a lot longer to compute it without the memoization. The memoization really cuts down on the amount of time that it takes to process that. Anyway, I thought that was a pretty interesting comparison that Shelley Powers uses in her book, JavaScript Cookbook. So I thought I'd include it as part of this to show the value of memoization when you want to use it. I hope you found that helpful. If so, please like the video. You can also find other tutorials on our website. They are organized by different categories, and you can go to our website to do that. If you'd like to watch another tutorial from our channel, just click the video link in the center of the screen. If you'd like to subscribe to our channel, we release new tutorials every week. Click the circle link on the left. To visit our website for those resources on JavaScript, click the link on the right. Thanks for watching.